And the first speaker is Tobias Hurth, who will talk about the uniqueness problem for global stationary solutions to the semi-discrete stochastic heat equation.
Thank you very much. Also, thank you for the invitation to speak here. I'd like to apologize for these technical problems that I've had. So this talk is about a project with Kostya Khanin and Beatriz Navarro-Lameda from Toronto. And in this talk, I will first introduce the semi-discrete stochastic heat equation. Then I will present our uniqueness result on this equation. And towards the end, we will discuss potential generalizations of the result. Could you please click? Thank you so much. So we start with the semi-discrete stochastic heat equation. The first equation you can see on this slide with a tag small s, capital S, H, E. This is essentially the heat equation. So you can see the classical form of the heat equation, to which is then added a noise. The size of the noise is determined by the parameter beta, the inverse temperature. And the noise is assumed white, in fact. So we have an IID collection of white noises. And what is particular here is that we look at the equation not in a continuous spatial setting, but on the integer lattice ZD. And so in particular, the white noises are assigned to the respective points on the integer lattice. And to the semi-discrete stochastic heat equation, one can then associate a Cauchy problem. This is often referred to as the parabolic Anderson model. Here, for a given initial time s and a given function, a given initial condition f defined on the integer lattice, we just try to solve the heat equation, assuming that at time s, the solution takes the form f. And okay, could you please click? Thank you. For the classical heat equation without any added noise, for the deterministic heat equation, by the Feynman-Katz formula, you can write down solutions using random walk, or in the case of a continuous space setting, using Brownian motion. And for the stochastic heat equation, something similar can be done. So in fact, here we'll consider a continuous time simple symmetric random walk called eta on the integer lattice. And we assume that the random walk evolves in a random potential. And this random potential is given by Brownian motions that correspond to the white noises we saw on the very first slide of this talk. Now, so we have an IID collection of Brownian motions. To each point on the integer lattice corresponds one Brownian motion. And then we can associate a random action to a path of the random walk. In some sense, you can say then that you have two layers of randomness. One layer is the random walk on the integer lattice, and the second layer is given by the noise, by the Brownian motions that constitute the random potential and that give rise to this random action, to this random weight. Now, if you click once more to the next slide, then this will help me to describe how the action is defined, in fact. This is a picture in 2 dimensions, but in fact, in this talk, we'll assume that the dimension of the integer lattice is 3 or higher, and that the inverse temperature beta is small. Now, imagine that the random walk starts at the point x0, that you can see more or less in the center of this picture. It's a continuous time simple symmetric random walk, so it will stay at its initial site for an exponential random time. And after this exponential random time, it will jump to one of its nearest neighbors. There are 2 times d of those nearest neighbors. It will pick one of them uniformly at random, jump to this side, then stay at the side again for an exponential random time, and so forth. And the action that is assigned to such a path is defined as follows. Now imagine that at the beginning, if you could go back maybe to, yes, thank you so much, to this slide. Imagine that at the beginning, you're at the side x naught. And we said before that there is a Brownian motion associated to this particular side. So at the initial time, the Brownian motion takes a certain value. And we stay at the side for some time until we jump. And we also record the value of the Brownian motion at the time when we jump, when we leave the site. This gives us 2 values for this Brownian motion. And we just compute the increment. We just compute the difference of these 2 values. Similarly, for the next point, x1, there is a Brownian motion assigned to this point as well. We record the value of this Brownian motion at the time when we arrive at the site. And we also record the value of the Brownian motion at the time we leave the site. We compute the difference and we add all of those differences. And if you could please go 1 slide back. Yeah, thank you so much. Now you see what I've just described in words. You see this also in the mathematical formula. In the center of the slide, the action is given indeed as a sum of increments of Brownian motions. The xj's are the points visited by the random walk, and the times sj and sj plus 1 correspond to the time when we arrive at the site xj and to the time when we leave the site xj. Right. And then going 2 slides further down, thank you. This setting leads us then to a way to define a solution to the Cauchy problem that we saw at the very beginning of this talk, to the parabolic Anderson model. We define what's called a point-to-point partition function. This will be a partition function that depends on the realization of the Brownian motions. In this sense, it is random, but we eliminate the other layer of randomness by averaging over the random walk. In particular, we will condition on the starting point and the end point for the random walk. We assume that at time s, the random walk starts at x, and we assume that at time t, it arrives at the point y. So this is like a bridge. We average over, well, the usual Gibbsian formalism, so exponential beta times the action associated to the random walk. And as we saw before, it's the action that also depends on the Wiener processes. So it's the action that is random as a function of the noise. And this is multiplied by the transition probability for the simple symmetric random walk. This is the small p. And it's also multiplied by a normalizing constant, this exponential factor e to the minus beta squared over 2 times t minus s. This is just so that we normalize appropriately, because otherwise this partition function would grow exponentially. And then we have the following results. This can be found, for example, in a monograph by René Carmona and Stas Molchanov from 1994. If the function f, the initial condition, grows at most exponentially, such a condition is needed already for the deterministic heat equation. We know that if we have initial data that grows very fast, then you can have multiple solutions to the Cauchy problem. But if f grows at most exponentially, then the function that is given here is the unique solution to the Cauchy problem that we saw at the very beginning. So the Cauchy problem for the semi-discrete stochastic heat equation. You can see this here. So it depends on the noise. It's a random solution. And what happens is you take your initial condition and then you average it with respect to the random point-to-point partition function that we saw earlier. This is what is happening. All right. Could you please move forward to the next slide? Thank you. Now, this Feynman-Katz formula that we saw on the previous slide, this formula for the solution to the Cauchy problem, in a very natural way gives rise to the following definition. Instead of trying to solve a Cauchy problem, we'd like to look for solutions to the semi-discrete stochastic heat equation that are in fact defined for all times. So global solutions in the sense of solutions that are defined for all times t in R in the real numbers. And to make this definition precise, we first introduce the space on which the noise lives. This is quite natural since we're talking about Brownian motions. We just take the Z default product of the two-sided Wiener space. That is the space of continuous functions on the real line that vanish at the origin. And as a probability measure on this space, we choose the Z default product of the two-sided Wiener measure. This is what we'll denote by Q. And then a global stationary solution to the semi-discrete stochastic heat equation will be a function that has two properties. The first property says essentially that the function is a solution to the heat equation. If you look at the term on the right, this is essentially what you get from the Feynman-Katz formula on the previous slide, where the initial condition is now the solution itself at time s. And then on the left, you get the solution at time t, when it has evolved further. And the second condition is physically a quite natural condition. You can describe this as stationarity in time. And what it says is that if you shift the Wiener processes in time, then this should not affect your solution. So if you have a particular solution that works for one random environment, then if you look at the solution for a time shift of the random environment, it should be essentially the solution as before, just shifted in time. So what matters is the random environment that the random walk sees, not so much at what time the random walk encounters this random environment. This is a way to think about this condition or to make sense of it. And moving on to the next slide, we'll see one very important particular global stationary solution that is also positive. Recall that we have defined the point-to-point partition functions where the random walk starts at a point x at time s and arrives at a point y at time t. And now we define what's called a point-to-line partition function, where we just sum over all the possible starting points. And then the Feynman-Katz formula implies, this is immediate, that this ZSYT solves the parabolic Anderson model if the initial data is just constantly equal to 1. And in fact, if we let S tend to minus infinity, then ZSYT will converge to a global stationary solution. This kind of makes sense if you think, or if you look at the following formula, which you can think of perhaps as a Chapman-Kolmogorov relation. So on the left-hand side, you assume that your random walk starts at time s somewhere at some point, and it wants to arrive at the point y by time t. And then you fix a time r that is strictly between s and t. And you can say that, well, to get the corresponding partition function, you sum over all possible points x where your random walk could be at time r. And then you multiply. in this formula, if you let s go to minus infinity, you see that you obtain exactly what we said was condition 1 before. Condition 1 to have a positive, to have a global stationary solution. So it makes sense to try to take the limit. And it turns out that if, as we assume, the dimension d is greater than or equal to 3, and if the inverse temperature beta is small, then this limit exists both in the sense of L2 convergence and in the sense of almost sure convergence. And in addition to that, it is positive almost surely. There's a dichotomy, in fact, this sort of as an aside, there's a dichotomy for partition functions. And in dimensions 1 and 2, for any inverse temperature beta, this limit exists almost surely, but it is 0. And it doesn't exist in the sense of L2. So there's no L2 convergence there. This is also called the regime of strong disorder in statistical physics. And in dimension 3 or higher, as long as the inverse temperature beta is small, you are in the so-called regime of weak disorder. And this regime is characterized by having a positive limit, almost surely. And in fact, as was shown in a discrete setting, but the proof is exactly the same in a discrete setting by CNI, you have L2 convergence, not just for Gaussian noise, but for noise that has a certain exponential moment. All right. And it is interesting, in fact, to study this limiting partition function, this object z minus infinity yt some more. There's still many interesting, we think, open questions related to its distribution. For example, for different types of noise, not just Gaussian noise. Is there a universality, for example, of the tail behavior? There are two tails that one can consider here. One is the tail at infinity, and then the tail as we approach 0. Or in other words, if you want to take the logarithm of this limiting partition function, the tail at minus infinity, then at plus infinity. What is known, for example, is that in the Gaussian case, all negative moments exist of this limiting partition function. However, you only have a certain finite number of positive moments. And presumably, if the noise has a bounded range, you will have a somewhat different situation where you have all positive moments. And moving on to the next slide.
Tobias, just a quick comment that you have very few minutes left.
Okay, yeah. So this is the main result. I'll just present this result. And in dimensions 3 or higher for small beta, that is in the regime of, in the weak regime, if Z is a positive global stationary solution to the equation, and if in addition we have the following growth condition, which means that it grows at most, it grows not quite exponentially, and it decays not quite exponentially either. Sub-exponential growth and decay, then almost surely the ratio of the solution is actually given by the ratio for this limiting partition function that we saw on the previous slide, z minus infinity yt. And maybe as a final remark, what are important assumptions here? We saw that dimension 3 or higher and beta small, this is essential, otherwise the limiting partition function would just be 0. The Gaussianity of the noise is used in our proof, but is perhaps not as essential. This is an interesting question to look into. And of course, we'd be interested in extending this result to the continuous space set. Thank you very much.